Good evening and welcome to Dreamy Academy. As we begin, I'd love to know where you're watching from tonight. Your city, your country, perhaps even what the night sky looks like outside your window. If you find peace and wonder in these quiet explorations of science, please take a moment to like the video and subscribe. It truly helps this little corner of thoughtful curiosity grow. To those already subscribed, thank you sincerely for being part of this slow and beautiful adventure. Tonight, we begin a journey into the heart of everything, into the fundamental architecture that gives form to the universe. It's a journey that asks us to stretch our imagination not across cosmic distances, but inward, into realms so impossibly small they defy our everyday senses. Consider for a moment the profound paradox of your own existence. You sit, you breathe, you listen, perceiving a world of solid objects, distinct forms, and tangible presences. Yet if we could truly see with the eyes of physics, we would discover that you and the chair beneath you and the air around you are almost entirely empty space. This isn't a poetic exaggeration, it's a precise scientific truth. The universe, at its most fundamental level, is not a collection of solid things, but a symphony of vibrating energy and probability, held together by forces we cannot see. Understanding this isn't just an intellectual exercise, it's an invitation to a deeper appreciation of reality. It's a quiet revelation that the world we inhabit, the very substance of our being, is far more mysterious and elegant than it appears. Chemistry, the subject we will gently explore together, is the patient study of this hidden architecture. It is the language through which the universe articulates its forms, from the simplest hydrogen atom to the most intricate protein molecule. It shows us how emptiness can feel solid, how invisible forces sculpt mountains and make hearts beat, how a handful of fundamental ingredients can combine in an almost infinite number of ways to create the rich tapestry of existence. There is profound beauty in this precision, a quiet wonder in understanding the unseen mechanisms that define our world. So let us begin our contemplative drift into the heart of matter itself, allowing the intricate dance of atoms to lull us into a deeper sense of peace and understanding. Have you ever paused to consider the very air you breathe, the chair you sit upon, or even the skin that holds you together? What is it truly that gives these things form and substance? Tonight we'll begin a journey inward, far beyond what the eye can see, into the fundamental architecture of reality itself. We'll explore the silent, ceaseless dance of the smallest constituents of matter, the atoms. They are the unseen architects, the tireless builders of everything. For millennia, thinkers have contemplated what lies at the very bottom of reality, what irreducible particles make up all the stuff we see. The ancient Greeks, with their keen minds, imagined atomos, indivisible units, so tiny they could never be cut. It was a beautiful, intuitive leap, a whisper of truth across millennia. Modern science, with its patient experiments and sophisticated instruments, has confirmed this intuition, though with far greater precision and an astonishing twist. These fundamental particles are not quite as solid as we might imagine. To truly grasp the scale of an atom, we must first learn to stretch our minds. Imagine a single grain of sand. It is small, certainly, but still visible, tangible. Now, imagine that grain of sand magnified to the size of a mountain, a grand peak reaching into the clouds. If that mountain-sized grain of sand were itself an atom, then the individual atoms within it would be no larger than tiny blueberries. They are almost impossibly small, existing at a scale that breaks our everyday comprehension. A single human hair is roughly 1,000,000 carbon atoms wide. To simply see an atom requires not just a microscope, but one that uses electrons rather than light, pushing the boundaries of what is observable. And yet, despite their minuscule size, atoms are not featureless points. They are intricate universes unto themselves, containing even smaller, more fundamental particles. At the very heart of every atom lies a dense, positively charged core called the nucleus. This nucleus is incredibly tiny, counting for almost all of the atom's mass, yet occupying only a vanishingly small fraction of its total volume, like a single pea in the middle of a vast cathedral. Within this dense heart are protons, which carry a positive electrical charge, and neutrons, which carry no charge at all. These particles are bound together with an almost unimaginable strength by a force known as the strong nuclear force, the most powerful force known in the universe, a cosmic glue that holds matter itself from flying apart. Around this incredibly dense nucleus, in a vast, mostly empty expanse, electrons dance. Electrons are far lighter than protons or neutrons, and they carry a negative electrical charge. Now, it is tempting to picture these electrons orbiting the nucleus like tiny planets around a sun, and indeed, early models of the atom often depicted them this way. But that picture, though a useful starting point, isn't quite right. The quantum world at these minuscule scales operates by rules that defy our macroscopic intuition. Electrons don't follow neat, predictable paths. Instead, they exist in probability clouds, regions of space around the nucleus where they are most likely to be found. They are less like distinct objects tracing orbits and more like a shimmering, fuzzy wave of potential, existing in multiple places at once, until observed. The atom, then, is a testament to the beautiful, bewildering strangeness of quantum mechanics. This leads us to the most astonishing revelation about atoms. They are almost entirely empty space. If the nucleus of an atom were indeed a pea at the centre of a vast cathedral, then the electrons would be like microscopic dust motes swirling somewhere within that cathedral, defining its outer boundaries. The space between the nucleus and the electron cloud is truly vast, a profound void. And yet, it is this very emptiness, orchestrated by the fundamental forces of electromagnetism, that gives rise to the solidity we perceive. The negative charge of the electrons and the positive charge of the protons create an electromagnetic field that acts like an invisible shield. When you touch a surface, your atoms don't actually collide with the atoms of the surface. Instead, the electron clouds around your atoms repel the electron clouds of the surface's atoms, creating the sensation of touch, of resistance, of solidity. It is a dance of invisible forces, creating the illusion of impenetrable matter. Every atom, from the lightest hydrogen to the heaviest uranium, is defined by the number of protons in its nucleus. This number, called the atomic number, gives each element its unique identity. A hydrogen atom always has one proton, a helium atom always has two, and so on, building the grand symphony of the periodic table, one proton at a time. The number of neutrons can vary, creating isotopes of the same element slightly different in mass but with the same chemical identity. The electrons, usually matching the number of protons, balance the charges, ensuring the atom is electrically neutral. This delicate balance of protons, neutrons, and electrons held together by fundamental forces across vast internal emptiness forms the stable fundamental building blocks of everything. There's a particular comfort in understanding that even the most solid-seeming things, the ground beneath your feet, the walls around you, your very own body, are, at their heart, a vast dancing emptiness, held together by invisible forces. The universe, it seems, builds its magnificent structures not from impenetrable blocks, but from shimmering patterns of energy and probability. This hidden architecture, this elegant simplicity, is what allows for the rich complexity of chemistry, and ultimately of life itself. So we've seen how atoms are the fundamental, mostly empty yet stable building blocks of matter. But if individual atoms are largely void and yet they form all the substances we know, how do they interact? How do these tiny probabilistic dancers connect with one another to form the vast array of molecules that make up our world? How does the invisible become visible, and how does the void become substance? That question of how atoms find each other and bind together will lead us into the quiet, powerful realm of the chemical bond. We left our contemplative drift with a profound question, didn't we? If atoms are, at their heart, vast expanses of emptiness, mere whispers of probability and vibrating energy, how then do they coalesce? How does this cosmic void give rise to the tangible, the solid, the very substance of our world, the chair you sit upon, the air you breathe, the intricate tapestry of your own being? The answer, dear friend, lies in what we call the chemical bond, the silent, invisible agreements that atoms forge with one another, transforming isolation into connection and potential into reality. Imagine, if you will, these unseen architects from our last journey. They are not solitary entities, content to drift in their individual probabilistic dances. No, there is a fundamental drive within them, an inherent quest for equilibrium, a yearning for stability. Think of it as a deep, resonant hum guiding their interactions. This quest for stability is often found in the arrangement of their outermost electrons, those vibrant, shimmering residents of the valence shell. These are the electrons that truly define an atom's social life, its propensity to interact, to give, to take, or to share. They are the diplomats, the negotiators, the ones who decide whether an atom will remain aloof or engage in the intricate ballet of bond formation. For most atoms, this yearning for stability translates into a desire to achieve a complete, symmetrical outer electron shell, often containing 8 electrons, a configuration we affectionately call the octet rule. It's like an atom striving for a state of perfect contentment, a harmonious balance where its energetic vibrations are most settled. To reach this serene state, atoms are willing to embark on extraordinary exchanges, to rearrange their electron clouds in ways that fundamentally alter their identities and create entirely new forms. Consider the 2 primary pathways to this electron-fueled contentment, these fundamental agreements that build the molecular universe. First, there is the dramatic, almost theatrical act of ionic bonding. Picture 2 atoms, each with its own unique energetic signature, approaching one another. One perhaps has a single, loosely held electron in its outermost shell, a lone dancer yearning to complete another's ensemble. The other atom, conversely, possesses a near-complete outer shell, lacking just 1 or 2 electrons to achieve its desired octet. In this scenario, a radical transfer occurs. The first atom, with a sigh of relief, donates its electron, letting it go entirely. It sheds this energetic burden, becoming a positively charged ion, or a cation, now boasting a stable, complete inner shell. The second atom, with an eager embrace, accepts this electron, completing its own outer shell and thus transforming into a negatively charged ion, an anion. It's a magnificent exchange, isn't it? A giving and a receiving that fundamentally alters both participants. But the story doesn't end there. Now these 2 newly formed ions, one positively charged and one negatively charged, are no longer neutral atoms. They are charged entities, and as you know from the fundamental laws of electromagnetism, opposite charges attract with an undeniable potent force. This powerful electrostatic attraction is the very essence of the ionic bond. It's a magnetic embrace, a strong, almost unbreakable tether that pulls them together, forming a crystalline lattice, a structured array of ions held in perfect shimmering balance. Think of table salt, sodium chloride, NaCl. A single sodium atom, Na, has 1 valence electron, while a chlorine atom, Cl, has 7. Sodium, in its quest for stability, readily sheds its lone electron, becoming a positively charged sodium ion, Na+. Chlorine, with equal eagerness, accepts that electron, becoming a negatively charged chloride ion, Cl. The resulting electrostatic attraction between Na+ and Cl is so strong that it forms the robust sparkling crystals we sprinkle on our food. It is a testament to the power of a single electron's journey, transforming two reactive elements into a stable essential compound. This is the architecture of the inorganic world, where vast networks of ions lock into place, building minerals, rocks, and the very bedrock beneath our feet. But not all atoms are so willing to part with or fully accept electrons. Many prefer a more democratic approach, a partnership born of mutual need and shared destiny. This, dear friend, is the realm of covalent bonding, a quieter yet equally profound agreement where electrons are not transferred, but rather shared. Imagine two atoms, each needing one or more electrons to complete its valence shell, but neither strong enough to forcefully take from the other, nor weak enough to simply give theirs away. What do? They compromise. They bring their electron clouds close enough so that their respective valence electrons can be shared between them, orbiting both nuclei simultaneously. These shared electrons now belong to both atoms, effectively completing the outer shells of both partners. This sharing creates a new, larger electron cloud that encompasses both nuclei and molecular orbital. That is a testament to their collaboration. The electrons are no longer solely associated with one atom, but are now a common property, binding the two atoms together in a stable, harmonious union. The attraction here isn't between oppositely charged ions, but rather the simultaneous attraction of the shared electrons to both positively charged nuclei. It's a delicate balance, a constant dance of attraction and repulsion that settles into a state of lower energy and greater stability. Consider the humble water molecule, H2O. An oxygen atom needs 2 electrons to complete its octet, and each hydrogen atom needs 1. Instead of a transfer, oxygen forms a covalent bond with 2 separate hydrogen atoms, sharing 1 electron with each. The electrons are constantly moving, but they spend enough time between the oxygen and hydrogen nuclei to create a strong, stable molecule. Or think of the oxygen you breathe, O2. 2 oxygen atoms, each needing 2 electrons, come together and share 4 electrons between them, forming a double bond, a truly intimate partnership. Methane, CH4, the primary component of natural gas, exemplifies carbon's ability to form 4 covalent bonds, reaching out to 4 hydrogen atoms, creating a perfectly tetrahedral molecule, a tiny, elegant structure. These covalent bonds are the very fabric of organic chemistry, the building blocks of life itself. From the simplest gases to the most complex proteins and DNA, it is the intricate network of shared electrons that weaves together the astonishing diversity of molecules that make up every living thing. They allow for flexibility, for intricate 3-dimensional structures, for the dynamic dance of chemical reactions within our own cells. And what a dance it is! Every time a chemical bond forms, energy is released. It's like atoms exhaling, settling into a more relaxed, stable state. Conversely, to break a bond, energy must be supplied, like coaxing atoms out of their comfortable embrace. This constant flux of energy, absorbed and released, is the very engine of chemistry, powering everything from the warmth of a burning log to the intricate metabolic pathways within your body. It is the silent, energetic pulse that animates the material world. So you see, the void is not truly empty. It is a canvas upon which these silent agreements, these energetic exchanges, are perpetually drawn. The solidity we perceive is not due to atoms physically touching like tiny billiard balls, but rather the robust, unwavering strength of these chemical bonds. It is the electromagnetic forces of shared and transferred electrons, the powerful attractions that arise from their strategic arrangements that create the illusion of substance. The resistance you feel when you push against a wall, the integrity of your own skin. Consider for a moment the profound paradox. The universe, at its most fundamental, is a symphony of vibrating energy and probability, yet through these elegant, almost poetic mechanisms of bonding, it constructs a world of undeniable form and function. From the fleeting interaction of a hydrogen atom with an oxygen atom to form water, to the vast, interconnected networks of molecules that constitute a forest or a human brain, it is all born from this deep inherent drive for stability, this continuous negotiation and collaboration among the unseen architects. We are not merely observers of this grand chemical ballet, we are integral participants. Every breath we take, every thought we conceive, every cell that regenerates within us is a testament to the ceaseless formation and breaking of these fundamental bonds. They are the invisible threads that tie together the micro and the macro, the ephemeral and the enduring. And in understanding them even just a glimpse, we begin to appreciate the profound elegance of reality, an invitation to a deeper appreciation of the quiet yet powerful architecture that underpins all existence. The void, it turns out, is simply waiting for atoms to make their agreements, to weave their magic, and to build the world anew, moment by moment. From the heart of the atom, where the void whispers promises of connection, we journeyed into the profound elegance of chemical bonds. We saw how the inherent quest for stability, the delicate ballet of electron sharing and transfer, transforms the vast emptiness into the perceived solidity of our world. Ionic crystals, robust and enduring, rise from the dramatic exchange of electrons. Covalent molecules, intricate and adaptable, weave the very fabric of life through shared possibility. Yet, as we stand at this threshold, a deeper mystery beckons. How do these fundamental bonds, these elemental acts of joining, blossom into the breathtaking complexity of molecules, and ultimately into the vibrant, pulsating tapestry of life itself? Consider for a moment the profound paradox. A simple line drawing on a page, representing a molecule, tells only half the story. It shows us which atoms are connected, yes, but it utterly fails to convey the three-dimensional reality, the exquisite architecture that truly defines its character. Just as a blueprint for a grand cathedral needs to convey not just the materials, but the spatial relationships, the soaring arches and intimate alcoves, so too do molecules possess a specific crucial geometry. This geometry is not arbitrary, it is a direct consequence of the electrons themselves, those shimmering, fuzzy waves of potential that orbit the nucleus. Imagine a group of dancers each needing their own space, yet bound together by an invisible force. They will naturally arrange themselves to maximize their distance from one another. In the molecular realm, it is the electron pairs, both those involved in bonding and those lone pairs that reside solely on a central atom that dictate this spatial arrangement. They repel each other, pushing and pulling until they find the most stable, most energetically favourable configuration. This is the essence of VSEPR theory, the valence shell electron pair repulsion theory, a beautifully simple concept that unlocks the intricate shapes of the molecular world. Take, for instance, a molecule like carbon dioxide, CO2. We might envision it as a straight line, OCXO. And indeed, in its linear elegance, the two oxygen atoms position themselves as far as possible from each other, 80 degrees apart around the central carbon. The electron pairs involved in forming those double bonds demand their space. But then consider water, H2O. If we only looked at its formula, we might picture it as linear too, like a tiny straight bridge. Yet water, the very elixir of life, is famously bent. Why? Because the central oxygen atom not only forms two covalent bonds with two hydrogen atoms, but also possesses two lone pairs of electrons. These lone pairs, occupying even more space than bonding pairs, exert a stronger repulsive force, pushing the hydrogen atoms closer together, creating that characteristic V-shape. It is this specific bent geometry that gives water its remarkable properties, allowing it to dissolve so many substances and play its central role in biological systems. Or think of methane, CH4, the simplest organic molecule. Here, a central carbon atom bonds with 4 hydrogen atoms. The electron pairs around the carbon repel each other equally, pushing the hydrogen atoms into a perfectly symmetrical three-dimensional shape, a tetrahedron. Each hydrogen is at the corner of a pyramid with the carbon at its center, with bond angles of precisely 109.5 degrees. This tetrahedral arrangement is not just aesthetically pleasing, it is fundamental to the architecture of carbon-based life, allowing for the vast, branching complexity of organic chemistry. Ammonia, NH3, offers another variation, a central nitrogen atom bonded to 3 hydrogens, but with 1 lone pair. That lone pair again distorts the perfect tetrahedron, pushing the hydrogens down to form a trigonal pyramidal shape, like a tiny 3-legged stool. These molecular shapes are not mere curiosities. They are the secret language through which molecules recognize and interact with one another. They are the keys that fit specific locks, the hands that offer a particular grip. But once these individual molecular architectures are formed, how do they converse? How do they gather, coalesce, and transform from individual entities into the liquids, solids, and gases we perceive? This brings us to the subtle, yet immensely powerful realm of intermolecular forces, or IMFs. While chemical bonds are the strong, unwavering ties within a molecule, the very glue holding atoms together, intermolecular forces are the gentler, often temporary attractions between distinct molecules. Think of chemical bonds as the sturdy beams and girders that construct a house. IMFs are the magnetic fields that allow houses to form a neighborhood, or the subtle currents that guide a fleet of ships. They are weaker, yes, but their collective power is immense, orchestrating everything from the boiling of water to the intricate folding of proteins. Let us explore these whispers and embraces. The most universal and often the weakest are the London dispersion forces, LDFs. Imagine an atom with its electrons constantly swirling and shifting. For a fleeting moment, these electrons might happen to cluster on one side, creating a temporary instantaneous dipole, a momentary imbalance of charge. This momentary dipole can then induce a similar temporary dipole in a neighbouring molecule, leading to a weak transient attraction. It's like a fleeting whisper, a momentary glance of recognition between strangers. Present in all molecules, LDFs are the sole intermolecular force for nonpolar molecules, and their strength increases with the size and number of electrons in a molecule. They are why even noble gases can be liquefied at very low temperatures. Moving up in strength, we encounter dipole-dipole forces. These arise in molecules that possess a permanent dipole moment, meaning one end of the molecule is always slightly positive and the other always slightly negative, due to unequal sharing of electrons in their covalent bonds. Think of the bent water molecule with its partial negative charge on the oxygen and partial positive charges on the hydrogens. The positive end of one water molecule will be gently attracted to the negative end of another. It's a more consistent, albeit still gentle magnetic attraction, a polite nod of recognition between acquaintances. But then there is a special, exceptionally strong type of dipole-dipole interaction, a force so vital it underpins life itself: hydrogen bonding. This occurs when a hydrogen atom, already covalently bonded to a highly electronegative atom like fluorine, F, oxygen, O, or nitrogen, N, finds itself attracted to a lone pair of electrons on another F, O, or N atom in a different molecule. It's not a full bond, but it's far stronger than other IMFs, more like a firm handshake or a gentle but persistent embrace. Water again serves as our quintessential example. The hydrogen atoms of one water molecule are powerfully drawn to the oxygen atom of another, forming a dynamic network of connections. This intricate web of hydrogen bonds gives water its unusually high boiling point, its remarkable surface tension, and its ability to expand upon freezing, a property crucial for insulating aquatic life in winter. Hydrogen bonds are also the very rungs of the ladder in the DNA double helix, the exquisite architecture that stores the blueprints of life. These intermolecular forces, in their collective dance, dictate the macroscopic properties of substances. They determine whether a compound is a gas, a liquid, or a solid at room temperature. They govern how easily a substance evaporates, how readily it dissolves, and how it interacts with biological systems. And this brings us to the very pinnacle of molecular complexity, the realm where subtle differences in three-dimensional arrangement lead to profoundly different outcomes. We arrive at the concept of isomers, molecules that share the exact same chemical formula, the same number and type of atoms, but differ in the arrangement of those atoms. Imagine having the same set of Lego bricks, but building two entirely different structures. Among isomers, a particular class, stereoisomers, captivates us with its elegance and its implications for life. Here, the atoms are connected in the same order, but their spatial orientation, their arrangement in 3 dimensions, is different. And among these, none are more fascinating than enantiomers, often called chiral molecules. Imagine your left hand and your right hand. They are mirror images of each other, yes? But try as you might, you cannot superimpose one perfectly onto the other. Your left hand will never fit perfectly into a right-handed glove. This handedness, or chirality, is a fundamental property of many molecules, particularly those with a carbon atom bonded to 4 different groups. Such a carbon is called a chiral center. The implications of chirality are profound, especially in the biological world. Our bodies, the proteins that catalyze our reactions, the enzymes that digest our food, the receptors that detect our senses, they are all exquisitely designed to interact with molecules of a specific handedness. One enantiomer of a drug might be a potent medicine, while its mirror image might be inert or even tragically toxic. Consider thalidomide, a notorious example from history. One enantiomer was an effective sedative, while its mirror image caused severe birth defects. Or think of the scent of spearmint versus caraway. Both are caused by enantiomers of the same molecule, carvone, yet our noses detect them as distinct aromas. Our taste buds too differentiate between the left-handed and right-handed versions of sugars and amino acids. Life itself is chiral, built almost exclusively from left-handed amino acids and right-handed sugars. So from the dance of electrons within a single atom, through the unwavering strength of chemical bonds, we arrive at a world of astonishing molecular architecture. We see how the repulsion of electron pairs sculpts molecules into precise functional shapes. We understand how the subtle whispers and firm embraces of intermolecular forces orchestrate the behavior of matter, giving rise to liquids, solids, and gases, and enabling the intricate machinery of life. And we gaze upon the profound elegance of chirality, where a mere mirror image can hold the key to health or illness, to flavor or fragrance, revealing the universe's preference for specific, intricate forms. The journey continues, ever inward, ever outward, revealing that the vast complexity we sought to understand is not a chaotic jumble, but a symphony of purposeful design, a meticulously choreographed dance of shapes and forces. We are beginning to discern the fundamental language spoken by the unseen architects, and with each new insight, the world around us and within us becomes a little more luminous, a little more wondrous. Our journey through the intricate architecture of molecules has unveiled a universe of purposeful design, a symphony where shape and subtle forces dictate the very nature of existence. We've seen how the unseen architects, the atoms, arrange themselves with elegant precision, and how their collective dance crafts everything from the simplest gas to the most complex proteins. But these molecules, these exquisite structures, are not static monuments. They are participants in a ceaseless dynamic ballet. Now, we invite you to shift your gaze from the fixed forms to the fluid transformations to the very heart of change itself, chemical reactions. Imagine a world not just of objects but of processes where old connections dissolve and new ones emerge, giving birth to entirely different substances with novel properties. This is the essence of chemistry in motion, the engine that drives every breath, every thought, every flicker of starlight. Consider the air you breathe, a delicate mixture of nitrogen, oxygen, and other gases. When you inhale oxygen, a molecule we know now as two atoms sharing electrons, enters your lungs. But it does not remain merely oxygen. Within the microscopic furnaces of your cells, it encounters glucose, a sugar molecule, itself a complex arrangement of carbon, hydrogen, and oxygen. What happens next is a marvel. The robust bonds holding the oxygen molecule together loosen. The intricate structure of glucose begins to flex and yield. Old friendships are broken, old partnerships dissolved only for new ones to form. Oxygen atoms find new companions in carbon and hydrogen, creating carbon dioxide and water, releasing a surge of energy that fuels your very being. This, in its simplest form, is a chemical reaction, a profound reordering of matter. At its core, a chemical reaction is nothing more and nothing less than the breaking of existing chemical bonds and the formation of new ones. It is a molecular dance of dismantling and reconstruction. We begin with reactants, the starting materials, and through this intricate choreography, we arrive at products, the new substances that emerge. The atoms themselves are never created or destroyed. They are simply rearranged, like a set of Lego bricks that can be assembled into an infinite array of forms. The universe, in its grand design, conserves its fundamental building blocks. But what impels these transformations? What is the driving force behind this constant flux? The answer, woven into the very fabric of existence, is energy. Every bond broken requires an input of energy. a gentle persuasion to release its hold. Conversely, every bond formed releases energy, a sigh of contentment as atoms settle into more stable arrangements. This exchange of energy defines the two fundamental types of reactions we encounter. Some reactions are like a warm embrace, releasing heat and light into their surroundings. These are more exothermic reactions, where the products are more stable and possess less stored chemical energy than the reactants. Think of a crackling fire, the combustion of wood releasing the sun's ancient energy as warmth. The atoms in the ash and carbon dioxide are in a lower energy state than they were in the wood and oxygen, and the excess energy is gracefully given back to the world. Then there are reactions that feel like a cool absorption, drawing energy from their environment to proceed. These are air endothermic reactions, where the products are less stable and hold more stored chemical energy than the reactants. Imagine an instant cold pack, where chemicals mix and absorb heat from your skin, leaving a chill in their wake. Here, the newly formed bonds are less stable, requiring an energetic subsidy to exist. Life itself, in its grand photosynthetic design, is a testament to endothermic processes, capturing the sun's radiant energy to build complex sugars from simple carbon dioxide and water. Yet, even a reaction that is energetically favourable, one that promises a release of warmth and stability, often doesn't spontaneously erupt. A log in the fireplace won't burst into flames without a spark. This initial nudge, this necessary push to overcome molecular inertia, is what we call activation energy. Imagine molecules as tiny spheres nestled in a valley, representing their current stable state. To transform into new products, they must first climb a small hill, a barrier, before they can tumble down into a new, lower valley of greater stability. That climb, that initial energetic investment, is the activation energy. It's the cost of entry to the dance, the moment of strain before the graceful pirouette. The higher the hill, the more difficult it is for the reaction to begin. So how do we encourage these molecular transformations? How do we provide that activation energy or make the climb easier? Several factors play a crucial role in dictating the rate at which a reaction proceeds. First, concentration. Imagine a crowded dance floor. The more dancers there are, the more likely they are to bump into each other and form new pairs. Similarly, increasing the concentration of reactants means more molecules are available to collide, increasing the chances of effective collisions that lead to bond breaking and forming. Second, temperature. Heat is essentially a measure of molecular kinetic energy. When we raise the temperature, molecules move faster, collide with greater frequency, and, crucially, with greater force. These more energetic collisions are far more likely to overcome the activation energy barrier, allowing the reaction to proceed more rapidly. Think of sugar dissolving faster in hot tea than in cold. Third, surface area. If a reaction occurs at the interface between two substances, like a solid dissolving in a liquid, increasing the surface area of the solid provides more sites for interaction. A lump of sugar dissolves slower than granulated sugar because the granulated sugar offers a vast expanse of surface for the water molecules to engage with. But perhaps the most profound and elegant facilitators of chemical reactions, especially within the delicate machinery of life, are catalysts. A catalyst is a substance that speeds up a reaction without being consumed in the process. It's like a wise guide who knows a hidden, gentler path over the activation energy hill, allowing molecules to transform with far less effort. Within living systems, these molecular guides are called enzymes, exquisitely shaped protein molecules that can accelerate reactions by factors of millions or even billions, ensuring that the biochemical processes essential for life occur at the right speed and under precise conditions. Without enzymes, the symphony of life would slow to a glacial, unworkable crawl. As we contemplate these dynamic transformations, we must also acknowledge that many chemical reactions are not a one-way street. Often as products form, they themselves can revert back into reactants. This dance back and forth continues until the rates of the forward and reverse reactions become equal. At this point, the system reaches a state of chemical equilibrium. It's a dynamic balance, not a cessation of activity. Imagine a bustling hallway where people are moving in both directions. At equilibrium, the number of people entering one side equals the number leaving the other, even though individuals are constantly in motion. The net change is zero, but the activity is ceaseless. This concept of equilibrium is profoundly important, especially in biological systems. Our bodies constantly strive to maintain a delicate balance of pH, of temperature, of nutrient levels. When a system at equilibrium is disturbed, perhaps by a change in concentration, temperature, or pressure, it will instinctively shift its balance to counteract that disturbance and re-establish a new equilibrium. This principle, known as Le Chatelier's principle, is the universe's elegant way of seeking harmony. If you add more reactants, the system will shift to make more products to consume the excess. If you remove products, the system will shift to make more to replace them. This constant subtle adjustment is a testament to the resilience and self-regulating nature of chemical systems. From the simplest combustion to the intricate metabolic pathways that sustain every living cell, chemical reactions are the very pulse of the universe. They are the means by which matter transforms, energy flows, and complexity emerges from simplicity. They are the unseen architect's grand performance, a continuous, breathtaking spectacle of creation and dissolution. As we observe these principles, we gain not just knowledge, but a deeper appreciation for the exquisite choreography underpinning reality. The breaking and forming of bonds, the whisper of energy, the subtle guidance of catalysts, the ceaseless dance of equilibrium. These are not abstract concepts, but the very mechanisms that allow the stars to burn, the oceans to teem with life, and your own body to breathe, think, and feel. This dynamic realm of chemical change is an invitation to witness the universe in its most active, most transformative state, a constant reminder that all things are in flux, and within that flux lies the very essence of existence. We have journeyed together through the intricate architecture of atoms, witnessed the formation of their steadfast bonds, admired the elegant geometry of molecules, and, in our last contemplative drift, observed the grand, transformative ballet of chemical reactions. We saw how the universe, in its tireless dynamism, continuously rearranges its elemental components, breaking old ties and forging new ones, a constant pulse of creation and recreation. But as we stand at the precipice of this understanding, a new, more profound question emerges, whispering from the depths of the microscopic. How much? How do we quantify this unseen dance? How do we measure the ingredients, predict the outcomes, and truly understand the scale of these atomic transformations? Imagine trying to count every grain of sand on a vast beach, or every star in a boundless galaxy. The individual units, atoms and molecules, are impossibly tiny, far beyond the reach of our senses, existing in numbers so astronomically vast that our everyday counting systems fail. To truly comprehend the symphony of matter, we need a new language, a bridge between the macroscopic world we inhabit and the subatomic realm where all this magic unfolds. This, dear friend, is where we introduce the concept of the mole. It is perhaps the most fundamental and profoundly elegant invention in the chemist's toolkit, a concept that might initially feel abstract but quickly becomes an indispensable key to unlocking the quantitative secrets of the universe. Think of it as the chemist's dozen, but a dozen of truly epic proportions. Just as a baker counts eggs by the dozen, we, as chemists, count atoms and molecules by the mole. 1 mole of any substance, whether it be water molecules, iron atoms, or even grains of sand if we could gather so many, contains precisely 6.022 and 10^23 particles. This colossal number, known as Avogadro's number, is not arbitrary. It is a fundamental constant of our universe, a testament to the elegant order that underpins all matter. To truly grasp its immensity, consider this. If you could count atoms at a rate of 100 per second, it would take you more than 80 trillion years to count 1 mole. If you were to spread 1 mole of peas over the entire surface of the Earth, the layer would be several meters deep. It is a number that humbles and astounds, an invitation to marvel at the sheer abundance of the microscopic world. The mole, then, is our translator. It allows us to bridge the unfathomable gap between the individual, invisible particle and the tangible, weighable substance. It transforms the abstract notion of 1 atom into a quantity we can actually work with in a laboratory, a quantity that has a measurable mass. This leads us quite naturally to the concept of molar mass. If you cast your gaze back to the periodic table, our cherished map of the elements, you'll recall that each element is assigned an average atomic mass. For carbon, it's approximately 12.01 atomic mass units, AMU. For oxygen, about 1600 AMU. The profound beauty of the mole is that this atomic mass, when expressed in grams, represents the mass of 1 mole of that element. So 1 mole of carbon atoms weighs 12.01 grams, 1 mole of oxygen atoms weighs 1600 grams, and for a compound we simply sum the atomic masses of all the atoms present in its chemical formula to find its molar mass. 1 mole of water H2O, for instance, weighs approximately 18.02 grams. 2 hydrogens at 101 geomole each, plus 1 oxygen at 1600 geosmol. The molar mass, therefore, becomes our Rosetta Stone, converting the invisible count of particles into a tangible weight. It allows us to say, with quiet confidence, if I weigh out 18.02 grams of water, I know I hold precisely 6.022 as 10^23 water molecules in my hand. This is not merely a practical tool, it is a philosophical revelation, a moment where the abstract becomes concrete, where the whisper of the atom can be felt in the palm of your hand. With the mole as our guide and molar mass as our scale, we are now equipped to truly understand stoichiometry, the grand accounting system of chemical reactions. Recall our balanced chemical equations from the previous chapter, those elegant arrangements of reactants transforming into products. We learned that the coefficients in front of each chemical formula ensure that atoms are conserved, a fundamental truth of the universe. But these coefficients are more than just balancing numbers. They are the precise mole ratios in which reactants combine and products are formed. Consider for a moment the formation of water from hydrogen and oxygen, 2H2G plus O2G, 2H2OL. This equation tells us that 2 molecules of hydrogen react with 1 molecule of oxygen to produce 2 molecules of water. But with the mole concept, this equation takes on a far more profound meaning. 2 moles of hydrogen gas react with 1 mole of oxygen gas to produce 2 moles of liquid water. This is the universe's recipe book, a meticulously detailed instruction manual for transformation. Just as a master chef follows a recipe, knowing that 2 cups of flour will yield a certain number of cookies, we, as chemists, can use these mole ratios to predict with astonishing accuracy how much of a product will form from a given amount of reactant, or how much of one reactant is needed to fully consume another. If we have, say, 4 moles of hydrogen, we know we'll need 2 moles of oxygen to react completely, and will produce 4 moles of water. We can then convert these mole quantities into grams using molar mass, allowing us to perform these calculations with substances we can actually weigh out in the laboratory. This is where the grand ballet of chemical reactions becomes a meticulously choreographed performance, where every participant knows their part and the quantities are precisely measured. Stoichiometry is the language through which we understand the quantitative art of chemical change, allowing us to not just observe but to predict and control the flow of matter. Yet the universe, in its beautiful complexity, rarely offers us perfect scenarios. In the practical world of the laboratory, or in the vast, sprawling reactions of nature, reactants are seldom present in the exact stoichiometric ratios indicated by a balanced equation. Often one reactant runs out before the others, putting a gentle yet firm limit on how much product can actually be formed. This is the concept of the limiting reactant. Imagine you are building magnificent molecular structures, perhaps tiny houses made of Lego bricks. Your recipe calls for 10 red bricks, 5 blue bricks, and 2 green bricks for each house. If you have an abundance of red and blue bricks, but only enough green bricks for 5 houses, then your green bricks are the limiting factor. You can only build 5 houses, no matter how many red and blue bricks you still possess. In a chemical reaction, the limiting reactant is the one that is completely consumed first, thereby stopping the reaction and dictating the maximum amount of product that can be formed. The other reactants, those still remaining after the limiting reactant is used up, are said to be in excess. It's a gentle reminder that even in the boundless potential of chemical transformation, there are finite boundaries, and the dance often concludes when one of its key performers gracefully bows out. Understanding the limiting reactant is crucial for optimizing reactions, ensuring efficiency, and minimizing waste, guiding us toward a more harmonious interaction with the material world. Finally, we arrive at the concept of percent yield, where the theoretical elegance of our equations meets the beautiful, sometimes messy reality of the laboratory. When we perform a stoichiometric calculation, we determine the theoretical yield, the maximum amount of product that could possibly be formed if the reaction proceeded perfectly, with 100% efficiency, no losses, and no side reactions. However, in the tangible world, perfect efficiency is a rare jewel. Reactions may not go to completion, some product might be lost during purification, or unwanted side reactions might consume some of our reactants, forming different products. The amount of product we actually obtain from an experiment is called the actual yield. The whole percent yield is simply a comparison of these two values, a measure of how successful our reaction was. Percent yield is actual yield, theoretical yield, x 100%. A percent yield of 100% means we achieved exactly what our calculations predicted, a rare and satisfying accomplishment. More often, we encounter yields below 100%, each percentage point telling a story of the practical challenges and nuances of chemical synthesis. It's an invitation to refine our techniques, to understand the subtle forces at play, and to constantly seek greater efficiency in our transformative endeavors. As we conclude this chapter, reflect on the profound journey we have undertaken. From the invisible dance of atoms to the precise measurement of their collective transformations, We have begun to decipher the universe's own operational manual. The mole, molar mass, stoichiometry, limiting reactants, and percent yield are not just abstract terms. They are the very language through which we quantify, predict, and ultimately control the endless permutations of matter. They allow us to move beyond mere observation to active participation, to truly learn the rhythm and measure of creation. We are not just observers, we become participants, learning the very rhythm and measure of creation, stepping closer to understanding the intricate quantitative harmony that orchestrates all that is. Having journeyed through the intricate dance of atoms, the architecture of their bonds, the geometry of their forms, the energy of their transformations, and the precise quantification of their movements, we now arrive at a new, yet equally fundamental landscape, the world of mixtures. Until now, we've primarily contemplated pure substances, those pristine entities composed of identical atoms or molecules. But consider for a moment the world outside your window, the air you breathe, the coffee in your mug, the very blood coursing through your veins. None of these are pure. They are a symphony of mingled components, a testament to chemistry's profound capacity for combination. Imagine a single pristine water molecule, its bent shape a tiny marvel of hydrogen and oxygen. Now imagine billions upon billions of these molecules, forming a droplet, then a pond, then an ocean. This is a pure substance. But what happens when we introduce a pinch of salt, a spoonful of sugar, or a breath of carbon dioxide into that water? We enter the realm of solutions, where disparate entities come together to form something new, yet retain their individual chemical identities. It is here, in these invisible seas of interaction, that much of life's chemistry, and indeed the chemistry of the cosmos, truly unfolds. We begin by distinguishing between the two broad categories of mixtures, heterogeneous and homogeneous. A heterogeneous mixture is one where the components are not uniformly distributed. Think of a handful of sand mixed with water. You can clearly see the distinct grains of sand suspended within the water. Or a salad, where each leaf, each crouton, each slice of tomato retains its visible individuality. The properties of a heterogeneous mixture vary from one point to another within the sample. A homogeneous mixture, however, is different. Here the components are uniformly distributed throughout, creating a single phase. If you were to take a sample from any part of the mixture, its composition and properties would be identical to a sample taken from any other part. This uniform distribution is the hallmark of a solution. When you dissolve sugar in water, the sugar molecules disperse so completely among the water molecules that the resulting liquid appears perfectly clear and consistent. You cannot distinguish the sugar from the water by sight alone. The sweetness, however, tells a different story. A story of intimate molecular entanglement. Within every solution we identify two key players, the solute and the solvent. The solvent is the component present in the largest amount, the medium that does the dissolving. It's often the substance that determines the physical state of the solution. Water, with its remarkable ability to dissolve a vast array of substances, is frequently referred to as the universal solvent. The solute, conversely, is the component or components present in lesser amounts, the substance that gets dissolved. When you stir sugar into water, water is the solvent, and sugar is the solute. When you breathe, nitrogen is the solvent in the air, and oxygen, argon, and carbon dioxide are solutes. But what orchestrates this invisible mingling? What determines if one substance will embrace another in a solution or simply push it away? The answer lies once again in the intricate dance of intermolecular forces, IMFs. Those subtle attractions we explored in Chapter 3. The guiding principle here is elegantly simple, yet profoundly powerful. Like dissolves like. This phrase, so often uttered in chemistry, is an invitation to consider the energetic compatibility between molecules. Polar solvents, like water, possess significant dipole-dipole forces and hydrogen bonding capabilities. They are eager to form strong attractions with other polar molecules or with ionic compounds, which, when dissolved, dissociate into charged ions, readily interacting with the solvent's partial charges. Imagine water molecules like tiny magnets, surrounding and pulling apart the ions of a salt crystal, or enveloping the polar hydroxyl groups of a sugar molecule, forming new, stable intermolecular bonds. This energetic exchange, this mutual attraction, is what drives the dissolving process. Conversely, non-polar solvents such as hexane or oil are dominated by weaker London dispersion forces. They readily dissolve other non-polar substances, forming new, equally weak, but energetically favourable London dispersion interactions. Oil dissolves oil, and grease dissolves grease. But try to mix oil and water, and you witness a dramatic refusal to mingle. The strong hydrogen bonds between water molecules are far more attractive to each other than to the non-polar oil molecules, which cannot participate in such strong interactions. The water molecules effectively squeeze the oil molecules out, forcing them to coalesce, creating those distinct layers we observe. Like dissolves like is not just a rule, it's a reflection of nature's preference for energetic harmony. Beyond the nature of the solute and solvent, other factors influence how much solute can dissolve. A temperature plays a significant role. For most solid solutes, increasing the temperature increases their solubility in a liquid solvent. Think of dissolving sugar in hot tea versus cold tea. The heat provides the kinetic energy needed to overcome the forces holding the solid together, and allows the solvent molecules to more effectively pull the solute apart. For gases, however, the opposite is true. Solubility generally decreases as temperature increases. This is why a warm soda goes flat faster than a cold one. The warmer temperature allows the dissolved carbon dioxide gas to escape more readily. Pressure, while having little effect on solid or liquid solubility, significantly impacts the solubility of gases. Higher pressure forces more gas molecules into solution, as evidenced by the fizz and pop when you open a carbonated drink, releasing the pressure. Once a solute is dissolved, we need a way to describe how much of it is present in a given amount of solution. This brings us to the crucial concept of concentration. Just as stoichiometry provided us with the language to quantify reactions, concentration gives us the language to quantify mixtures. Knowing the concentration is vital for everything from manufacturing pharmaceuticals to performing precise laboratory experiments, from understanding biological processes to ensuring the safety of drinking water. A medicine's efficacy depends on its precise concentration, just as the rate of a chemical reaction is often tied directly to the concentration of its reactants. Among the various ways to express concentration, one stands as the undisputed champion in chemistry. Molarity, M. Molarity is defined as the number of moles of solute per litre of solution. Here, we beautifully bridge our understanding of the mole from Chapter 5 with the practical world of solutions. Molarity equals moles of solute, litres of solution. This simple ratio is incredibly powerful. If you have a 1.0 m solution of sodium chloride, it means that every litre of that solution contains exactly 1 mole of NaCl. This allows us to directly connect the volume of a solution to the number of particles, moles, of the solute it contains. For instance, if you need 0.5 moles of a reactant for an experiment, and you have a 2.0 m solution of that reactant, you can calculate precisely what volume of the solution you need to measure out. It simplifies the accounting of particles in liquid environments, transforming a seemingly abstract quantity into a tangible, measurable reality. Let's consider a practical application. Dilution. Often in the lab or in industry, we prepare concentrated stock solutions for storage, and then, as needed, we dilute them to a lower concentration for specific applications. Dilution involves adding more solvent to a solution, which decreases the concentration of the solute but does not change the total number of moles of solute present. If you have a specific number of sugar molecules in a small amount of water and then add more water, you still have the same number of sugar molecules, but they are now spread out over a larger volume, making the solution less sweet, less concentrated. The relationship between initial and final concentrations and volumes during dilution is elegantly captured by the equation M1V1 = 2V2, where M1 is initial molarity, V1 is initial volume, M2 equals final molarity, V2 equals final volume. This equation is a cornerstone for preparing solutions of desired concentrations. It reminds us that the total moles of solute, mx5, remain constant during dilution, merely redistributed. Finally, as we dissolve substances in water, we uncover another fascinating characteristic: their ability to conduct electricity. We classify solutes into two main categories based on this property: electrolytes and non-electrolytes. An electrolyte is a substance that, when dissolved in a solvent, typically water, produces a solution that conducts electricity. This conductivity arises because the solute dissociates or ionizes into mobile ions, charged particles that can carry an electrical current. Strong electrolytes like ionic compounds, e.g. NaCl, KBr, or strong acids, e.g. HCl, H2SO4, dissociate almost completely into ions, making their solutions excellent conductors. Weak electrolytes such as weak acids, e.g. acetic acid, or weak bases, e.g. ammonia, only partially dissociate, resulting in solutions that conduct electricity poorly. A non-electrolyte, in contrast, is a substance that dissolves in a solvent but does not produce ions. Its solutions, therefore, do not conduct electricity. Most molecular compounds, particularly organic ones like sugar, sucrose, or alcohol, ethanol, are non-electrolytes. When sugar dissolves in water, the individual sugar molecules simply disperse throughout the water. They do not break apart into charged species. This distinction between electrolytes and non-electrolytes is not merely an academic point. It is profoundly important for biological systems. Our bodies rely on a delicate balance of electrolytes, sodium, potassium, calcium, magnesium ions, to regulate nerve impulses, muscle contractions, and fluid balance. Without these invisible conductors, the very spark of life would falter. As we conclude this exploration of solutions, take a moment to reflect on the unseen activity occurring within every glass of water, every drop of rain, every cell in your body. It is an intricate, dynamic world where molecules constantly interact, forming and breaking transient bonds, driven by the subtle forces of attraction and repulsion. Solutions are not static mixtures. They are vibrant, ever-changing environments where the principles of chemistry come alive, enabling the complex transformations that shape our world. From the vast oceans to the minutest biological reactions, the invisible sea of solutions is where the magic of molecular interaction truly manifests, an invitation to a deeper appreciation of reality's exquisite complexity. We have journeyed together through the invisible sea of solutions, observing how substances dissolve, how their particles mingle, and how the very presence of ions can transform a placid liquid into a conductor of unseen currents. We have seen the elegance of molarity, the precision of dilution, and the quiet power of electrolytes. Now, let us drift a little deeper into this aqueous realm, for within its shimmering depths lies another profound and dynamic interplay, the exquisite dance of acids and bases. Consider, if you will, the very fabric of existence, from the cellular machinery within your own body to the grand geological processes shaping our planet. At the heart of countless reactions, both vital and destructive, is this fundamental partnership. The acid and the base, forever seeking a delicate balance, forever exchanging a tiny potent particle. The proton. You've encountered them, perhaps without conscious thought, in the tartness of a lemon, the bite of vinegar, or the smooth, slippery feel of soap. These are not mere sensations, they are whispers from the microscopic world, telling tales of molecular structure and the relentless pursuit of stability. We are not merely learning about chemical categories, we are uncovering a language, a set of rules that govern an immense portion of the chemical universe. Let us begin with a foundational understanding, a gentle introduction to these two profound forces. Imagine an acid as a generous giver, a molecule poised to shed a tiny, positively charged hydrogen ion, a proton in essence, into its surroundings. This proton, a nucleus stripped bare of its electron, is a restless entity, eager to find a partner. The presence of these liberated protons is what lends an acid its characteristic tang and its capacity to etch and transform. Conversely, picture a base as an eager receiver, a welcoming embrace for that very proton. It possesses a structure, often an excess of hydroxide ions, OH, or simply a lone pair of electrons, ready to accept and neutralize the wandering proton. This acceptance often results in the formation of water, a testament to the elegant simplicity of their union. The slippery feel of a base is its own tactile signature, a different kind of interaction with our senses. This initial understanding, often attributed to Svante Arrhenius, offers a beautiful starting point. He proposed in a wonderfully insightful leap that acids are substances that produce hydrogen ions, H+, when dissolved in water, and bases are substances that produce hydroxide ions, OH, in water. Think of hydrochloric acid, HCl, dissolving in water. It dissociates, releasing H+ and Cl ions. Or sodium hydroxide, NaOH, a strong base, dissolving to yield Na+ and OH ions. It's a clear, concise picture, like the initial brush strokes on a vast canvas. However, the world of chemistry, much like the universe itself, often reveals layers of complexity and subtlety as we delve deeper. The Arrhenius definition, while foundational, has its limitations. What about substances that behave like bases but don't contain hydroxide? This is where Johannes Brønsted and Thomas Lowry, working independently, gifted us with a more expansive and elegant perspective. They invited us to view the interaction not just as the production of ions, but as a dynamic transfer of that tiny, potent proton. In their vision, an acid is a proton donor, and a pole base is a proton acceptor. This seemingly small shift in perspective opens up a vast new landscape. Now, A molecule can be a base, even if it doesn't have an OHE group, as long as it can accept a proton. Ammonia, NH3 for instance, readily accepts a proton from water, making it a base, even though it contains no hydroxide. This Bronsted-Lowry framework also introduces us to the concept of conjugate acid-base pairs. When an acid donates its proton, what's left behind is its conjugate base, now capable of accepting a proton back. Similarly, when a base accepts a proton, it transforms into its conjugate acid. It's a beautiful symmetrical dance. An acid and its partner base, a base and its partner acid, always linked by the presence or absence of a single proton. Water itself becomes a fascinating player in this drama, capable of acting as both a proton donor, an acid, and a proton acceptor, a base, a truly amphoteric molecule, adapting to its chemical company. As with all things in the chemical realm, not all acids and bases are created equal. Some are bold and decisive, completely dissociating or ionizing in water, releasing all their protons or hydroxide ions with a fervent abandon. These are our strong acids and strong bases. Hydrochloric acid, sulfuric acid, sodium hydroxide, they're committed to their role, leaving virtually no original molecule undissociated. Their strength lies in their complete surrender of the proton or their complete acceptance capacity. Then we encounter the more hesitant, the more equilibrium-driven players, the weak acids and weak bases. Acetic acid, the very essence of vinegar, is a classic example. When dissolved in water, only a small fraction of its molecules donate their protons. The vast majority remain intact, existing in a dynamic equilibrium with their dissociated ions. This partial dissociation is a hallmark of weakness, and it means that weak acids and bases are often gentler, more forgiving in their interactions, yet no less significant in their roles. Think of the buffers in your blood, tirelessly maintaining a precise pH, almost entirely composed of weak acid-base pairs. This brings us to one of the most elegant and universally recognized measures in chemistry, the pH scale. It is a testament to the power of logarithmic thinking, allowing us to quantify the immense range of hydrogen ion concentrations that exist in solutions, from the fiercely acidic to the gently basic. The P in pH stands for power of, specifically the negative logarithm base 10 of the hydrogen ion concentration. Why a logarithm? Because the concentration of H+ ions can vary by many orders of magnitude, a millionfold, a billionfold, or even more. A linear scale would be unwieldy, impossible to visualize. The pH scale condenses this vast range into a manageable spectrum, typically from 0 to 14. A pH of 7 is considered neutral, signifying a perfect balance between H+ and OH ions, as found in pure water at room temperature. A pH below 7 indicates an acidic solution, meaning a higher concentration of H+ ions. The lower the number, the more acidic it is. Conversely, a pH above 7 denotes a basic or alkaline solution, where the concentration of OH ions outweighs that of H+. The higher the number, the more basic it is. Consider the profound implications of this scale. A change of just one pH unit represents a tenfold change in hydrogen ion concentration. This means a solution with a pH of 3 is 10 times more acidic than a solution with a pH of 4, and 100 times more acidic than a solution with a pH of 5. This exponential sensitivity underscores the critical importance of pH regulation in everything from industrial processes to the delicate biochemistry of living cells. Our blood, for instance, maintains a remarkably narrow pH range of 7.35 to 7.45. Even slight deviations can have severe, life-threatening consequences. When an acid and a base meet, particularly a strong acid and a strong base, a remarkable event occurs, a neutralization reaction. It is a beautiful chemical ballet where the aggressive H+ ions from the acid combine with the accepting OH ions from the base to form the most stable and ubiquitous molecule, water, H2O. The remaining ions, often a cation from the base and an anion from the acid, come together to form a salt. For instance, when hydrochloric acid meets sodium hydroxide, they produce water and sodium chloride, common table salt. This is not just a theoretical concept, it's the principle behind antacids calming an upset stomach, or the careful adjustment of soil pH for optimal crop growth. It is chemistry in action, bringing balance to a system. And what of those vigilant guardians of pH, the buffers? Imagine a system designed to resist change, to absorb the shock of added acid or base without dramatically altering its fundamental character. That is the essence of a buffer solution. Typically composed of a weak acid and its conjugate base, or a weak base and its conjugate acid, buffers work by having both a proton donor and a proton acceptor readily available. If you add a small amount of acid, the conjugate base component of the buffer soaks up the extra protons. If you add a small amount of base, the weak acid component donates protons to neutralize the added hydroxide. This intricate partnership allows the solution to maintain a relatively stable pH, a testament to molecular foresight and the elegance of equilibrium. Without these tireless molecular custodians, life as we know it, with its precise enzymatic reactions and delicate cellular environments, would simply not be possible. As we conclude this exploration into the world of acids and bases, we are left once again with a profound sense of the universe's intricate design. From the searing intensity of concentrated acids to the gentle, life-sustaining balance within our own bodies, the dance of protons is a fundamental rhythm. It reminds us that even the simplest exchange of a subatomic particle can dictate the properties of matter, shape landscapes, and sustain the very breath of life. We have moved from the unseen architects of atoms to the invisible sea of solutions, and now to the dynamic, proton-driven interactions that define much of our chemical reality. Each step unveils a deeper layer of understanding, an invitation to a deeper appreciation of reality's quiet complexities. The journey continues, always revealing new wonders, new questions, and new connections in the grand tapestry of chemistry. Having journeyed through the intricate architecture of atoms, the intimate embrace of chemical bonds, the elegant ballet of molecular geometry, and the profound equilibrium of acid-base interactions, we arrive now at a truth as fundamental as it is astonishing. The universe hums with an invisible current, a ceaseless exchange that underpins life, decay, and the very flow of energy. We speak of redox reactions, a term that might sound formidable, yet describes the most elegant and essential dance of electrons, a silent, powerful conversation happening everywhere, all the time. Remember how we first encountered the electron, a shimmering, fuzzy wave of potential responsible for the apparent solidity of matter and the very formation of bonds. Now, let us return to this tiny, tireless dancer, for it is in its graceful transfer that much of the universe's work is accomplished. Consider for a moment the profound paradox. Electrons, so infinitesimally small, are the very agents of grand transformation. They are the currency of energy exchange, the unseen threads connecting the slow decay of a fallen leaf to the explosive brilliance of a star. This is not merely a concept to be memorized. It is an invitation to witness the dynamic pulse of reality itself, a pulse that beats within you, within the air you breathe, and within the very ground beneath your feet. The term redox is a portmanteau, a gentle merging of two complementary actions, reduction and oxidation. These two processes are inseparable, two sides of the same coin, a cosmic give and take that must always occur simultaneously. One atom cannot gain an electron without another atom losing it. It is a fundamental law of balance, an exquisite choreography of matter and energy. Let us unpack these terms with the quiet reverence they deserve. Oxidation, in its most fundamental chemical sense, is the loss of electrons. Imagine an atom content in its electron cloud suddenly releasing one or more of these tiny charges. It has been oxidized. Think of it as an act of generosity, a giving away of a precious resource. When an atom loses electrons, its positive charge effectively increases, or its negative charge becomes less negative. We often use the mnemonic oil rig, oxidation, I. Conversely, reduction is the gain of electrons. The atom that accepts those freely given electrons is said to be reduced. It is an act of reception, a welcoming of new energy. When an atom gains electrons, its positive charge effectively decreases, or its negative charge becomes more negative. And so the other half of our mnemonic, reduction. Together, these two processes form a redox reaction. An electron leaves one atom and in the very same breath finds a new home with another. It is a continuous, universal rhythm, a perpetual motion machine of the microscopic world. To help us track these electron shifts, chemists employ a clever bookkeeping system called oxidation states, or oxidation numbers. These are not actual charges in many cases, but rather hypothetical charges assigned to atoms in a molecule or ion, assuming that electrons in a bond are completely transferred to the more electronegative atom. It's a way to quantify the electron ownership and identify who is losing and who is gaining. For example, in elemental form, atoms have an oxidation state of 0 as they share electrons equally. But when they bond, particularly with atoms of differing electronegativity, these numbers shift. If an atom's oxidation state becomes more positive, it has lost electrons, it has been oxidized. If its oxidation state becomes more negative, it has gained electrons, it has been reduced. It's a subtle yet powerful tool to trace the invisible currents. Now, let us consider the roles within this electron transfer drama. The substance that causes another substance to be oxidized is called the oxidizing agent. In doing so, the oxidizing agent itself gains electrons and is therefore reduced. It is the electron acceptor, the one that pulls electrons away. Conversely, the substance that causes another substance to be reduced is called the reducing agent. In doing so, the reducing agent itself loses electrons and is therefore oxidized. It is the electron donor, the one that offers its electrons. It's a beautiful symbiotic relationship. The oxidizing agent cannot reduce without the reducing agent oxidizing, and vice versa. They are inextricably linked in this fundamental dance of energy. To truly grasp the ubiquity and profound significance of redox reactions, let us turn our gaze to some examples, both grand and intimate, that shape our world and our very existence. Consider the flickering flame of a candle or the roaring inferno of a forest fire. This dramatic release of heat and light is a redox reaction par excellence. combustion. In these reactions, a fuel, often a hydrocarbon like wax or wood, rapidly combines with oxygen from the air. The carbon and hydrogen atoms in the fuel are oxidized. They lose electrons to oxygen, while the oxygen atoms are reduced. They gain electrons from the fuel. This rapid electron transfer releases a tremendous burst of energy, a testament to the stored potential within chemical bonds. It is a powerful, almost violent demonstration of how these electron shifts can transform matter and unleash energy. Now shift your focus from the dramatic to the slow, relentless march of time. Observe an old iron gate, its surface dusted with a reddish-brown powder. This is corrosion, specifically the rusting of iron. Here, iron atoms slowly give up their electrons to oxygen atoms in the presence of water. The iron is oxidized, gradually transforming into iron oxide rust, a fragile, crumbling testament to its electron loss. The oxygen in turn is reduced. This is a redox reaction unfolding with quiet inevitability, a patient dismantling of structure, returning matter to a more stable oxidized state. It is a slow, contemplative dance of decay, yet no less powerful in its ultimate transformation. From decay, let us turn to creation, to the controlled harnessing of this electron flow. Pick up a remote control or glance at the glowing screen of your phone. What powers these devices? Batteries. A battery is an ingenious device designed to separate the oxidation and reduction half reactions, forcing the electrons to travel through an external circuit, your device, before completing their journey. Within the battery, one material is constantly being oxidized, losing electrons at the anode, while another is constantly being reduced, gaining electrons at the cathode, creating an electric current. It is a testament to human ingenuity, channeling the invisible electron river to power our modern world. Here, the dance is not wild and free, but carefully choreographed, yielding power on demand. But perhaps the most profound and intimate example of redox reactions lies within you. Within every breath you take, every thought you think, every beat of your heart. We speak of biological respiration. This is the intricate process by which your cells extract energy from the food you eat. Glucose, a simple sugar, is slowly and systematically oxidized. Its carbon and hydrogen atoms gradually lose electrons. Simultaneously, the oxygen you inhale is reduced or accepting those electrons to form water. This controlled multi-step electron transfer releases energy in small manageable packets, which your body then uses to fuel all its life processes. It is a quiet, continuous symphony of electron movement, sustaining the very spark of consciousness, transforming the chemical potential of a meal into the vibrant energy of life itself. Consider the sheer elegance of it all, from the explosive power of combustion to the slow, patient decay of rust, from the harnessed energy of a battery to the intricate life-giving processes within your own cells. All are variations on the same fundamental theme, the transfer of electrons. These tiny unseen particles are the silent architects of change, the tireless carriers of energy, orchestrating the ebb and flow of matter throughout the cosmos. This understanding of redox reactions is not just another chapter in our journey. It is a lens through which to view the world with renewed wonder. It reveals the interconnectedness of all phenomena, showing us that the seemingly disparate processes of burning, rusting, generating electricity, and living are all manifestations of this ceaseless electron dance. It is a reminder that even at the most fundamental level, reality is not static, but a vibrant, dynamic interplay of giving and receiving, a constant flow of energy and transformation. As we conclude this exploration, allow yourself a moment to simply feel this truth. Feel the quiet hum of electrons within your own being, within the air around you, within the very fabric of existence. It is a subtle yet profound invitation to a deeper appreciation of reality's exquisite complexity and the fundamental currents that power it all. What further secrets, we might wonder, does this invisible energy flow hold, waiting to be unveiled? We have journeyed through the intricate dance of electrons, witnessing their profound power as they transfer between atoms, igniting the very processes of transformation we call redox reactions. We've seen how these tiny, unseen shifts are the lifeblood of everything from a flickering flame to the quiet hum of a battery, from the slow decay of rust to the rapid pulse of life itself. It is a universe in constant motion, driven by these minuscule exchanges. But now, let us pause and consider a deeper layer of this cosmic ballet. The why. Why do some reactions unfold with an effortless grace, almost eager to transform, while others demand a constant input of energy, a persistent nudge to move forward? Why does a log burn, releasing its stored energy in a blaze of light and heat, yet a pile of ash never spontaneously reassembles itself into wood? This brings us to the very heart of chemical thermodynamics, the study of energy and its transformations in chemical systems. Imagine, if you will, energy as the universal currency, traded in every interaction, every bond formed, every bond broken. Just as we explored the physical architecture of molecules, we must now delve into their energetic landscapes. Every atom, every molecule, possesses an inherent energy content, a kind of potential, much like a stretched spring or a rock poised at the edge of a cliff. When chemical bonds rearrange, this energy landscape shifts, either releasing energy into the surroundings or absorbing it from them. We touched upon this earlier, speaking of exothermic reactions, which liberate heat, warming their surroundings, and endothermic reactions, which absorb heat, leaving their environment feeling cooler. These describe the change in a property we call enthalpy, represented by the symbol dH. It is in essence the heat content of a system at constant pressure. A negative dH signifies an exothermic process, a release of energy, often felt as warmth. A positive dH marks an endothermic journey, an absorption of energy, often perceived as cold. Many reactions we witness daily, from the simplest combustion to the complex metabolic pathways within us, are driven by a favourable enthalpy change, a desire to shed excess energy and settle into a more stable, lower energy state. Yet enthalpy alone does not tell the whole story of spontaneity. If it did, every exothermic reaction would occur effortlessly, and every endothermic one would be impossible without external aid. But we know this isn't always true. Ice melts spontaneously at room temperature, absorbing heat, an endothermic process. Water evaporates, also endothermic. Yet it happens all around us. There must be another, equally powerful driving force at play. This brings us to one of the most profound and perhaps most poetic concepts in all of science: entropy. Imagine a pristine, perfectly organized library, every book in its designated place. Now, imagine a gentle breeze wafting through an open window, scattering a few papers. Then a child enters, pulling books from shelves, leaving them haphazardly on the floor. Eventually, without conscious effort, that library tends toward a state of disarray. This natural tendency towards disorder, toward the dispersal of energy and matter, is entropy. Entropy, symbolized as ds, is a measure of the randomness, disorder, or the dispersal of energy and matter within a system. The universe, in its grand, inexorable march, tends towards states of greater entropy. Think of a single drop of ink introduced into a clear glass of water. It doesn't remain a perfect, concentrated sphere. Instead, it diffuses, spreading its colour throughout the entire volume. This is an increase in entropy. The ink molecules are more dispersed, occupying a greater number of possible arrangements. Consider the molecules of a solid, tightly packed and vibrating in fixed positions. As you add energy, heat, they gain enough kinetic energy to break free and move past each other as a liquid, a more disordered state. Add more energy, and they escape entirely as a gas, wildly chaotic and spread out, the most disordered state. Each transition from solid to liquid to gas represents an increase in entropy. This isn't just about physical states, it's about the number of ways energy can be distributed and the particles can be arranged. A system with more ways to arrange its components, or more ways to distribute its energy, has higher entropy. The universe whispers this truth to us constantly. Things tend to fall apart, to spread out, to become less ordered, unless energy is actively expended to maintain their order. Your meticulously tidied desk will, given enough time and neglect, accumulate papers, pens, and forgotten coffee cups in a glorious entropic crescendo. It's not a malevolent force, it's simply the most probable state for things to be in. So we have two powerful, often competing forces: enthalpy, which favours reactions that release energy and lead to lower energy states, often more stable bonds, and entropy, which favours reactions that increase disorder and spread out energy. How do we reconcile these two to predict whether a reaction will occur spontaneously? This is where the genius of Josiah Willard Gibbs enters, with his elegant solution, Gibbs free energy, denoted as DG. Gibbs free energy combines the effects of enthalpy and entropy, weighted by temperature, into a single predictive value for spontaneity. The equation is beautifully simple yet profoundly powerful. dG equals dH. TDS. Here, dG is the change in Gibbs free energy, dH is the change in enthalpy, T is the absolute temperature in Kelvin, and ds is the change in entropy. Let's unravel what this equation tells us. If dG is negative, dG 0. The reaction is spontaneous. Under the given conditions, this means it will proceed without continuous external energy input. It is an exergonic reaction, meaning it releases energy that can be used to do work. Think of a ball rolling downhill. It happens naturally. If dG is positive, dG 0. The reaction is non-spontaneous under the given conditions. It will not proceed on its own. It requires a continuous input of energy to occur. This is an endergonic reaction. Imagine pushing a ball uphill. It requires constant effort. If dG is 0, dG equals 0. The system is at disequilibrium. There is no net change as the forward and reverse reactions are occurring at equal rates. Now let's look at how enthalpy and entropy play their roles. 1. When dH is negative, exothermic, and ds is positive, increasing disorder. Both factors favour spontaneity. The reaction will always be spontaneous, regardless of temperature. This is the ideal scenario for a reaction to proceed easily. Think of combustion. It releases heat and creates many gaseous products, high disorder. 2. When dH is positive, endothermic, and ds is negative, decreasing disorder. Both factors disfavour spontaneity. The reaction will never be spontaneous. It will always require energy input. Think of synthesizing complex biological molecules from simple precursors. It requires energy and creates order. 3. When DH is negative, exothermic, and DS is negative, decreasing disorder. Here, enthalpy favors spontaneity, but entropy disfavors it. The spontaneity depends on the temperature. At low temperatures, the TUS term is small, so the favorable DH dominates, and the reaction can be spontaneous. Example: water freezing below 0°, releases heat, increases order. Chapter 4. When DH is positive, endothermic, and DS is positive, increasing disorder. Here, enthalpy disfavors spontaneity, but entropy favors it. Again, spontaneity depends on temperature. At high temperatures, the /TUS term becomes large and negative, potentially overriding the positive DH, making the reaction spontaneous. Example: water boiling above 100 degrees absorbs heat, increases disorder. Consider for a moment the profound paradox inherent in these laws. Life itself, in all its astonishing complexity and order, appears to defy the universe's relentless push towards disorder. We build intricate cells, tissues, and organisms constantly fighting against the tide of entropy. But this apparent defiance is an illusion. Life doesn't violate the second law of thermodynamics, the law of increasing entropy. It simply exports its disorder. We take in highly ordered food molecules, break them down, increasing the entropy of those molecules, and release heat and waste products, increasing the entropy of our surroundings to maintain our own internal order. We are, in essence, tiny, temporary pockets of order in a universe that is constantly, beautifully, and inevitably winding down towards maximum disorder. This understanding of Gibbs free energy allows us to predict and, crucially, to control chemical reactions. It is the fundamental principle behind designing efficient energy systems, from the batteries that power our devices, where spontaneous redox reactions generate electricity with a negative dG, to the fuel cells that promise cleaner energy. It explains why photosynthesis, the very bedrock of life on Earth, is a non-spontaneous process, positive dG, that requires a continuous input of solar energy to create the ordered glucose molecules from simpler carbon dioxide and water. Conversely, cellular respiration, the process by which organisms extract energy from glucose, is a highly spontaneous negative dG redox reaction that releases the energy needed to drive life's activities. This principle extends its silent influence to every corner of your existence. The way your body metabolizes nutrients, the synthesis of proteins, the transmission of nerve impulses, all are governed by the delicate balance of enthalpy and entropy, quantified by Gibbs free energy. It's the invisible hand that guides the universe's transformations, ensuring that some paths are taken readily, while others require a persistent push. As we conclude this chapter, reflect on the vast implications of these thermodynamic laws. They are not merely abstract equations. They are the very rules by which the universe plays, dictating its direction, its energy flow, and ultimately its destiny. They offer us a glimpse into the grand sweep of cosmic change, from the formation of stars to the fleeting existence of life, all moving within the boundaries set by the dance of energy and disorder. It is an invitation to a deeper appreciation of reality, where even the most complex phenomena are rooted in these elegant fundamental principles. We are not just observing reactions, we are observing the universe's deepest inclinations, its drive towards equilibrium, its quiet, constant unfolding. What further secrets does this energetic landscape hold for us? The journey continues, ever inward, ever outward, revealing more layers of its magnificent design. And so our contemplative drift continues, doesn't it? We've journeyed through the intricate dance of atoms, explored the steadfast embrace of chemical bonds, and watched as molecules arrange themselves into myriad forms, each with its own subtle influence. We've witnessed the tireless breaking and remaking of these bonds in the grand theatre of chemical reactions, learned to quantify their players, and navigated the invisible seas of solutions where acids and bases perform their exquisite ballet. Most recently, we peered into the very heart of why these transformations occur, unraveling the profound principles of thermodynamics, the universal laws of energy and disorder that orchestrate all existence. We saw that the universe, in its magnificent design, leans towards a certain kind of freedom, a gentle unraveling, a spreading out of energy. We understood that spontaneity isn't merely about releasing heat, but about achieving a greater dispersal of energy, a quiet kind of liberation. The Gibbs free energy, that elegant equation, offered us a glimpse into the very will of the cosmos, a prediction of what can happen, what wants to happen given the right conditions. But as we reflect on this energetic landscape, a new question naturally arises, doesn't it? If the universe has a will, if reactions have a drive, how do they express it? How do we, as observers, truly see and understand these unseen architects, these probabilistic dancers, these tiny, vibrant entities that govern our reality? What are the tools that allow us to perceive the shimmer of an electron, the vibration of a bond, the very essence of matter itself? The answer, dear companion, lies in light, and in the profound, almost mystical realm of quantum mechanics. Remember, back in our very first whispers, we spoke of electrons not as tiny planets orbiting a nucleus, but as a shimmering, fuzzy web of potential, a probability cloud. That wasn't just poetic license. It was an early hint at a truth so deep, so counterintuitive that it shattered the classical worldview of physics. Today we step fully into that truth, into a world where the rules we know from our macroscopic existence simply dissolve. Imagine, if you will, shrinking down not just to the size of an atom, but into the very fabric of its being. Here in this impossibly small realm, the familiar certainty of objects with definite positions and speeds vanishes. We enter a domain governed by probabilities, by waves, by an inherent fuzziness that defines existence itself. This is the realm of quantum mechanics, the very language of the subatomic. Consider for a moment the profound paradox. Everything we perceive as solid, as real, is built from these quantum entities, yet they refuse to behave like anything solid or real that we know. An electron, for instance, isn't just a particle, it's also a wave. It possesses what we call wave-particle duality. It can diffract and interfere like a wave, yet it can also be detected as a discrete particle. It doesn't choose, it is both simultaneously until we try to observe it. This inherent ambiguity leads us to one of the most famous and mind-bending principles of quantum mechanics, Heisenberg's uncertainty principle. It tells us quite simply that we cannot simultaneously know both the precise position and the precise momentum, mass times velocity, of a particle like an electron. The more accurately we try to pin down its location, the less we know about where it's going, and vice versa. It's as if the act of observation itself changes the reality, blurring the lines, ensuring that the universe always holds a whisper of mystery close to its chest. This is why our electron is a probability cloud. We can only speak of the likelihood of finding it in a certain region of space, not its exact trajectory. From this wave-like nature, from solving the intricate mathematical equations known as the Schrödinger equation, emerge the fundamental descriptors of an electron's life within an atom, the quantum numbers. These aren't just arbitrary labels, they are the elegant, precise addresses and characteristics of an electron's allowed energy states and spatial distributions. We begin with the principal quantum number, n. This is like the Main Street address, defining the electron's primary energy level and its average distance from the nucleus. The higher the n known, the higher the energy, and the further out the electron tends to reside. Then comes the azimuthal or angular momentum quantum number, Lais. This is like the house number on that street, but it also describes the shape of the electron's orbital. For L0, we have an s orbital, a perfect sphere, like a tiny shimmering pearl. For Uls equal 1, we find p orbitals, shaped like dumbbells, 2 lobes on opposite sides of the nucleus. As L increases to 2 for d orbitals, then 3 for f orbitals, the shapes become increasingly complex and beautiful, multi-lobed structures, like intricate molecular sculptures. Next, the magnetic quantum number, mml, specifies the orientation of these orbitals in space. If the p orbital is a dumbbell, L tells us if it's aligned along the x or z axis. It's the subtle tilt, the precise angle that gives each orbital its unique spatial identity. Finally, the spin quantum number, ms, describes an intrinsic property of the electron itself, often visualized as a tiny magnetic field generated by its spin, either spin up +1, 2, or spin down a 1, 2. It's a fundamental characteristic, like a tiny internal compass. These 4 quantum numbers, taken together, provide a unique fingerprint for every electron in an atom, ensuring that no 2 electrons in the same atom can have the exact same set of quantum numbers, a principle known as the Pauli exclusion principle. It's the universe's way of maintaining order amidst the probabilistic chaos. These atomic orbitals, the s, p, d, and f shapes, are not rigid boundaries, but rather regions of space where the probability of finding an electron is highest. They are the true forms of the probability clouds we first encountered, and it is the precise arrangement and overlap of these orbitals that dictates how atoms interact, how they form the chemical bonds we explored in Chapter 2, and ultimately, how molecules assume their specific 3-dimensional architecture, the bent shape of water, the tetrahedral geometry of methane. All are elegant consequences of the quantum mechanical dance of electrons within these orbitals. But what truly brings these invisible quantum states to life, allowing us to perceive them, is their interaction with energy, specifically light. Electrons, you see, are not static within their orbitals. They exist in discrete energy levels, much like steps on a ladder. An electron cannot hover between steps. It must occupy one specific rung or another. When an atom or molecule absorbs a specific quantum of energy, a photon of light, an electron can jump from a lower energy level to a higher one. This is called an excitation. It's like gently nudging a ball up to the next step. However, this excited state is often unstable. The electron, yearning for its ground state, will eventually fall back down to a lower energy level, and when it does, it releases that absorbed energy in the form of another photon of light. This is emission. Crucially, the energy of the photon absorbed or emitted is exactly equal to the difference in energy between the 2 quantum levels. This means that each atom, each molecule has its own unique set of energy transitions, its own characteristic fingerprint of light it can absorb or emit. And this, dear friend, is where spectroscopy enters our story. The magnificent art and science of listening to the universe's whispers of light. Spectroscopy is our window into the quantum world, our way of interpreting the symphony of vibrating energy that is matter. Imagine shining a beam of light through a sample. If the sample contains atoms or molecules with energy differences that match the energy of the incoming photons, those photons will be absorbed. By measuring which wavelengths of light are absorbed and to what extent, we can deduce the electronic structure, the types of bonds present, and even the concentration of substances within the sample. This is the essence of absorption spectroscopy. Think of the vibrant colours we see when white light, a mixture of all visible wavelengths, hits a leaf. The chlorophyll molecules within absorb the red and blue light for photosynthesis, reflecting the green light back to our eyes. We perceive green. A substance's colour is simply the light it doesn't absorb. Conversely, if we excite atoms or molecules, perhaps by heating them in a flame or bombarding them with electrons, they will emit light as their electrons fall back to lower energy states. This emitted light, when passed through a prism, separates into a unique spectrum of discrete lines, a barcode of colours specific to that element. This is emission spectroscopy. It's how we identify elements in distant stars, how fireworks get their brilliant hues, and how forensic scientists can identify trace elements at a crime scene. Each element sings its own unique song of light. But spectroscopy isn't limited to visible light. The electromagnetic spectrum, stretching from long radio waves to incredibly short gamma rays, is a vast ocean of energy, and each region interacts with matter in a different way, revealing different secrets. Ultraviolet visible UV-vis spectroscopy, for instance, probes electronic transitions, giving us insights into the electron clouds and conjugation within molecules, crucial for understanding organic dyes and biological pigments. Infrared IR spectroscopy focuses on the vibrational modes of molecules. Imagine the bonds between atoms as tiny springs. They can stretch, bend, and twist. Each type of bond, CH, OH, CO, vibrates at a characteristic frequency. When infrared light of that specific frequency hits the molecule, it gets absorbed, exciting that particular vibration. By analysing the fingerprint of absorbed IR frequencies, we can identify the functional groups present in a molecule, a cornerstone of organic chemistry. And then there's nuclear magnetic resonance, NMR spectroscopy, a technique of incredible power and subtlety, which exploits the magnetic properties of atomic nuclei, those tiny spins we mentioned. By placing a sample in a strong magnetic field and irradiating it with radio waves, we can induce transitions in the nuclear spins. The precise frequencies absorbed reveal the chemical environment of specific atoms within a molecule, allowing chemists to determine the complete structure of complex organic compounds with astonishing detail. It's like being able to map out every single atom and its neighbours in a molecule. So you see, the quantum mechanical understanding of electrons and their energy levels is not merely abstract theory. It is the very foundation upon which we build our most powerful analytical tools. It allows us to perceive the unseen architects of reality, to understand how they are structured, how they bond, and how they transform. It is through the language of light that we read the story of matter. Consider the profound implications, the stability of every chemical bond, the specific geometry of every molecule, the very existence of life itself. All are ultimately governed by the probabilistic wave functions of electrons and their quantized energy levels. The energetic landscapes we discussed in thermodynamics, the drive for reactions to occur, are ultimately realized through these precise quantum leaps and falls. This journey into the quantum realm is perhaps the most humbling and awe-inspiring of all. It invites us to shed our classical preconceptions and embrace a reality far stranger, far more elegant, and far more interconnected than we could have ever imagined. It reminds us that at its most fundamental level, the universe is not a collection of solid, predictable objects, but a shimmering, vibrating tapestry of energy and probability, a symphony of light and matter playing out across the vastness of existence. As we conclude this chapter, let us hold on to this sense of wonder. For in understanding the quantum nature of reality, we don't just learn about chemistry, we learn about the very essence of what it means to observe, to know, and to participate in the magnificent, ever-unfolding mystery of the cosmos. Our journey continues, now with an even deeper appreciation for the subtle yet profound interplay of energy and matter, and the light that illuminates it all.